Perfect circles work great, don't they, Ed? Just think of the wheel.
Yeah, so why even bother with something like an ellipse?
The importance of the ellipse wasn't fully recognized until the 1600s, when Johannes Kepler proved that the 6 known planets traveled in elliptical orbits around the Sun.
Oh, what did I say?
We've seen a plane slice through the cone to reveal a circle. Then, as the angle of the cut became steeper, the elongated shape of the ellipse was revealed. The equation for a circle of radius 5, centered at the origin, was x squared plus y squared equals 25. Essentially, the elongated shape of an ellipse results when a circle undergoes a dilation transformation. So let's derive an equation for the ellipse from the equation for the circle. Here's a list of some of the points on the circle. If we apply a dilation that stretches the circle in the vertical direction, the image is an ellipse. Each of the original points now has a corresponding image point. The y-coordinates of the image points are 5 times the y-coordinates of the original circle. The dilation is t, mapping xy onto x5y. So the ellipse is really just the circle stretched vertically by a factor of 5. To find an equation for the ellipse, we start with this relationship. Its y-coordinates are 5 times the original y-coordinates. We can restate it this way. The original y is 1/5 of the image y. So each point xy on the image corresponds to the point x, y over 5 on the original. And since x, y over 5 is a point on the circle, x squared plus y over 5 squared must equal 25. This is the equation for the ellipse. Notice that even though the transformation is a stretch of the circle, the y term in the equation is actually reduced by a factor of 5. The circle can also be stretched horizontally. In this case, the transformation stipulates a multiple of x instead of y. When this transformation is applied to the original circle, the y-coordinates remain the same, but the x-coordinates are multiplied by a factor of 2. This results in another ellipse, and we can find its equation using the previous example as a model. That transformation mapped y onto 5y and didn't affect the x. In the equation, we saw that the y term had been replaced by a y over 5 term. Now we have a transformation that maps x onto 2x. So, to arrive at the equation for this new ellipse, we simply replace the x term in the original circle's equation with x over 2. This equation can be verified by plugging in some sample x values and solving for the corresponding y values. Now we'll do an example where the transformation affects both the x and y coordinates. T maps xy onto 3x4y. It's another dilation transformation. When applied to the original circle, the circle is stretched both vertically and horizontally, and the resulting shape is another ellipse. Following the pattern established before, we can find the equation of the new ellipse. Since x is mapped onto 3x, the x term must be x over 3 squared. And the y term must be y over 4 squared. This is the equation of the ellipse, but we will now rewrite the equation in what is known as standard form. We can expand the x and y terms to give x squared over 9 plus y squared over 16 equals 25. Dividing both sides of the equation by 25 gives us this equation. Both terms can now be factored, giving this result. To understand why this is called standard form, we must examine the unit circle and determine what dilation would produce an ellipse with this equation. Following the earlier pattern, the dilation must map xy onto 15x20y. Let's call the 15 the horizontal stretch factor and represent it by b. 20, the vertical stretch factor, we'll call a. If this general transformation is applied to the unit circle, then the equation of the image ellipse is x squared over b squared plus y squared over a squared equals 1. Examining the graph of this general equation reveals some characteristics of the ellipse. The x-intercepts are b and negative b. The y-intercepts are a and negative a. In this case, the length 2a is known as the major axis of the ellipse, and 2b is the minor axis.
I figured it out, Ed. We can do our time travel right here. Just mention the name of a conic section, and hey, it's magic time.